I'll raise in this talk. So this is based on two papers. One actually just came out today in collaboration with Song He and Jia Kai Guo, which is actually in the audience. And in a bit more broader picture, I think the question that we're posing is, oops. Okay, the question that they were posing is that when physicists think about amplitudes, and in the back of our mind, when we say that we imagine that we have the answer, the answer that we have kind of have the feeling of that for example, the L loop amplitude, it's summing over some transcendental functions, multiplying some rational functions, where the rational functions may be there for various symmetry purposes. For example, it might be there to have the correct quantum number, to absorb the little group weight, to have the correct even conformal inversion properties. And so we basically extract out something that takes care of all of those constraints. And then we just have something, for example, for n equals 4 super ML, this will be just something that is dual conformal invariant. And then we talk about what are the possible functions here. And the question that I want to raise in this talk is essentially, is this actually true? Is this expectation actually true? True in the meaning that do we actually expect always that the amplitude, the answer actually separate into this kind of product structure? If it does, what are the general properties we can say about this function here? Is it always rational? Is it, or is it at most contain square roots? And moreover, which is probably like one of the main questions that we can raise in this conference is how does this kind of picture actually emerge from all of these geometry constructions that we have for the amplitude? How does this kind of picture actually emerge? So just to give a little bit idea of how this emerges, let's just take one geometry, for example. So let's just take one of the main characters in this conference, the amplituhedron. So let's look at amplituhedron and see how does this picture emerge. So I don't think I need to give any more introduction. So we know that basically in amplituhedron, we have the positive Grassmannian going over under the amplituhedron map. We mapped into this Y space. And this Y space is space is characterized by positivity condition, which reflects that we expect that this geometry has only local boundaries. And we have further having these sign flip conditions to further characterize this geometry. Now in this talk, actually it will be more convenient for me not to think about Y. Okay, so I'm gonna avoid writing Y. So the way that you can avoid writing Y is to project your bosonized twister. So we project the bosonized twister into its complement. So there's going to be the big Z, which is a bosonized twister, and then I project into this complement. So I'm going to call it little z. So of course, this is basically the same because we're taking the determinants, or we're really looking at the complement of the big Z's in the Y space. So these two conditions just collapse into conditions that you oppose on your 4 brackets. Okay, so it's just I plus 1 JJ plus 1 is bigger than 0, and 1, 2, 3 I having K sign flips. So, okay, good. So this is what I will call the tree region. Okay, this is just Tn. So this is just a tree region, which is basically this only involves information about your kinematics. Now, of course, this gives you the space. So if you're just interested in tree level, then this gives you the geometry for your tree level amplitude, and you compute the canonical form for this geometry, and you get the tree amplitude. But we're interested in the all loop amplitude, and the all loop amplituhedron in this language essentially is that besides the tree part, we start to introduce line and twister space, which represents your loop degrees of freedom. And the loop geometry is basically you just have lines that are with I plus 1 is bigger than 0. There's also self-positive, and they also have the respective sign flipping conditions. So this collection defines the loop amplitude. But now, by just looking at it the way that I'm writing it, it's very clear that you can split this into 2 parts. One part is just the kinematic part, which just defines a region in your kinematic space. And then you have the loop part, which you have these lines in twistor space, and you define a 4L form in this space. So if I view it in this kind of two pieces point of view, then essentially what I'm doing is that I'm looking at a region here. So this is my kinematic space, which I call T and my pre-region. And then at any point, so anything that is satisfied this at any point in here, I'm attaching a loop geometry. That's another way of viewing this. So at each point in my kinematic space, I'm attaching a loop geometry because obviously any point that satisfies this, I can construct my 4L form. And then I have my loop geometry. So, okay, now we see that this picture is starting to emerge. So we see that the amplitude is actually, you're having a base here, which is the tree level geometry. And at each base, you're attaching a loop geometry. And you can compute the canonical form of that loop geometry. Now, so it looks like it wants to be in a product form. So the first question you can ask is this product trivial in the sense that it's the same loop form multiplying the entire tree region? In other words, is the geometry a direct product? And the answer is, of course, obviously no, right? Because we know already in the very beginning, that there's actually multiple different pieces of these in n equals 4 invariant we will call R invariants or Yang-Yin invariants here. There's multiple different Yang-Yin invariants. So it's more like individual pieces of Yang-Yin invariant multiplying some loop corrections to it. So it cannot be an overall direct product. So that we already know. So what do we expect? Well, what we expect is that we can define, so this is where we can start to define chambers. So how do you define chambers? So basically what we're doing is that we're just looking back at this Tn, and we can compute, without knowing anything, in principle, you can just find an arbitrary point here and compute this loop form, and then compute this loop form. I mean, you start to move around, and you ask the question, since you know that it's not a direct product, you can ask that if I start from here and you move around, what are the regions in which the loop form is the same? And until which part the loop form starts to differ. And just by thinking of that, that tells you that a natural way to view this whole construction is that, in principle, my tree region should be a union of different chambers. And here, the working definition of chamber is that within a given chamber, the loop form is homogeneous in the sense that you move inside the chamber, the loop form is the same. Once you move outside the chamber, you switch a chamber to another boundary, to another chamber, then you have a different loop form. And therefore, the loop geometry then becomes a sum of products instead of a direct product. It becomes, in a sense, a sum of products. Now, of course, this is just a direct working definition. We can immediately ask questions. Yes, please.
Yes, I'd like to ask a question. I mean, this sort of, maybe can you, the thing that I would sort of expected geometrically would be not that there'd be like one piece where it looks like one thing and one piece where it looks like something else, but rather that like, as you move, it sort of keeps changing. And if you take a small enough area, then it sort of is locally, maybe looks the same, but when if you like travel around globally and you come back where you started, you find that, you know, like you can't, the reason, like what I'm saying is that often I would say in geometry, the reason that you can't trivialize it isn't because it looks like one thing over here and it looks like something else over here, but just that like it's a feature of the fact that it's sort of continuously changing such that, you know, if you come back where you started, you can't the reason you can't flatten it out isn't because it's like changing dramatically from like one place to another, but just that it by the time you get back where you started, you find that you're in a different place. Can you address whether is the kind of intuition that I'm trying to express just wrong, or?
I think that right now our understanding is that we can look at the explicit answer and see what happens.
Okay.
Yeah,
super.
and so basically what happens, at least at the current, for all the examples that we see so far, is that, well, first of all, when I'm moving, of course, so here I think that I need to clarify. So certainly when I'm moving around here, of course, I'm putting different points in here. So the form, of course, will change because it depends on the external point. So here, by what I mean by the form changing or not changing is that once I uplift once I write the form in the general four bracket way, is it actually looks the same in the four brackets, just plugging in different kinematics. If that's what's happening, then it's the same form. And so basically what happens is that or we will see in a field example later, is that basically for each chamber, the form is the same, and at the boundary, the two form agrees at the boundary. And so this is basically what I see. Now, of course, notice that this is a loop by loop statement. So actually, this is part of the question that one can pose. So let me just put, okay.
I have a brief comment. Maybe intuitively, you have a projection, for example, from a polytope to another smaller polytope, and then you consider fibers. Maybe this chamber is where the fiber will like isomorphism, so maybe look like a quadrilateral, but then when you switch from one chamber to another, then the fiber will look like a triangle.
Okay, yeah, okay, that's
So,
great. Okay, thank you. Yeah.
that's
the
the transition, I think.
Okay.
Okay, yeah. Right. Good,
Is there any nice numerology of chambers, like,
you mean the combinatorics?
like how many there are?
We have, I'll just show an example, it grows fast, but yeah, so I mean, that's one of the things that we want to understand. But okay, so I just raised three questions. First of all, obviously is what are the boundaries of these chambers? We already know that what the boundaries of Tn is the usual local boundary. So what is the boundaries of the chambers? And what are actually the forms associated with each chamber? And probably the most important question is actually, does the chamber dissection terminate? Meaning that, of course, I'm looking at a particular loop level form. So if I look at one loop, it dissects into these different chambers. If I go to two loop, is it going to become more and more dissect? And is it asymptoting to an infinite number of chambers, or actually it actually terminates? So that's the question that one can pose. And just to answer a few of these, just try a preliminary answer, we can look at the first non-trivial case for amplitudes, the first non-trivial case, which is for k equals one loop and 6 points. So this would be 6 point next to MHV. And essentially, so this is the tree region. You can understand the tree region using filings of BCFW cells. So we know that there's two different tilings. You can use what I call 1, 3, 5 cells to do this tiling, and you can do 2, 4, 6. So this kind of numeration is associated with which of the minors of your Grassmannian is 0. But okay, so we know that there's these these two different tilings, and it turns out, at least at one loop, if you compute the loop form, the chambers are basically given by the intersections of these tilings. So basically that, so for example, so this region here will fall both in the image of BCFW cell 1 and BCFW cell 2, and then this region will have its own loop form. The boundary essentially is all the BCFW boundaries. Okay, so this is what the one loop next to MHB chamber looks like. So first of all, let's look at this region here. So if we look at the boundaries, it has 5 boundaries. So the usual BCFW cells has 3 local boundaries and 2 spurious boundaries at this case. And for the chamber, because of these intersections, it inherits all of the spurious boundaries that you get from BCFW cell 1 and 2, and actually only has 1 local boundary. Okay. Now, of course, you can compute its form, and what you would expect is that if you compute the chamber form here, here, and here, all of these 3 forms should add up to your BCFW, the image of your BCFW cell, or the form of that image. And indeed, that is the case. Individually, this is the form that you get. It's just a reflection of the fact that you have these 3. Now, of course, importantly, which is one of the things that is interesting that when you start to think of this, is that this is not, in some sense, this is not, the chamber forms are not a good object because they're actually not Yang invariant. Okay, I mean, of course, because they don't fall into the image of any cell, so they're not actually a Yang invariant. They actually dissect Yang invariants. But it's actually, I think it's a very interesting point of view, because in amplitudes, as you know, essentially Yangian invariance is doing us nothing. Because when we compute things, everything that falls out are automatically Yangian invariant. So Yangian invariant is not imposing any constraint on your amplitude. But now the picture that we have here is that we have all of these chambers. Each of these chambers have their own loop form, so their loop form is actually distinct. But more importantly, that the Yangian action acting on these chamber form are not trivial, because they're not invariant. Some of them are invariant, but of course individually they're not invariant. So this is a very interesting question to explore. Yes.
How do you see that it's not Yangian invariant from this formula?
You have to act on it, but just because we know that all the Yangian invariants are images of, you can prove that are images of the pository cell, and these are not images of any single cell. So you can use that argument to say that it's not invariant. Now, so what is actually the loop form? Okay, so in this context, you can say that the chambers, there's another role that the chambers are identified. They can be viewed as the intersection of BCFW cells. So at this level, you can either say that's either the intersection of BCFW cell, or there's an alternative way of saying what it is. It's basically the set of maximal cuts that are positive. So in each of these kinematics point for the amplitude, you can compute its maximal cut. So this is since the loop form is a 4 form. So here by maximal cut, I'm looking at the codimension 4 boundary. I look at these codimension 4 boundaries and I ask whether or not they reside within the amplituhedron or not. The set of cuts in which they reside in the amplituhedron, that actually, the set of cuts that are positive are actually different for each of these chambers. So this is an alternative way. And in fact, the later way of saying things is immediately leads to what exactly are the chamber forms, because so this is the 1 mass box and the 2 mass heavy, this is the 1 mass box, this is a 2 mass hard integral, and the presence of these things in your chamber form is directly reflecting the correct set of cuts that are positive. And we expect that because of course the way that we're defining these chambers are using the whether or not the loop form changes. So this kind of operation is more likely to generalize to a general point. So about how many chambers? So we can just look at the next point, k equals 1, n equals 7. So this next dimension 7 point. It's very easy to enumerate these chambers, because first you just enumerate. If you just work with the BCFW cells, there's 21 BCFW cell. And by using that, if 2 BCFW cells are involved within a given triangulation, then they of course cannot overlap. Using this information, and you can compute basically the overlapping structure of your BCFW cell. And you in the end you'll get 71 chambers for this for one loop. And we can also compute the boundary. So it's interesting. You can compute the boundary of these chambers. And so unlike because we do expect that this doesn't generalize, because in the previous n equals 6, as I mentioned, that the boundary of these chambers basically inherit all the spurious poles of your individual BCFW cell plus a local pole that they share. This is no longer true as you go to 7 point. At 7 point, basically you can see that only a subset of spurious boundaries are part of your chamber boundaries, along with its its shared local boundary. So already of course, we're trying to continue to analyze this, but as you can see, that to answer some of our questions within the realm of amplitude is a little bit difficult, because there's just so many chambers. In particular, what do we want to answer? For example, we know that at a certain point, we're going to have to go outside of BCFW cell just by looking at using the solutions to the maximal cut, because as I mentioned previously, that you can also see that the loop form actually is controlled by the maximal cut. And if you see generic maximal cut, you're going to be involved, you're going to encounter 4K cells whose intersection number is not 1. And so these will eventually have to be involved in your chamber. And how do these boundaries how do you determine these boundaries, and what do these boundaries play in your chamber? And that's probably what Marcus was mentioning before, not in the viewpoint of chamber, but really that these boundaries are very interesting for us. But really the beast is that we know that the amplitude actually has elliptic functions. And we know that there's elliptic, eventually we're going to get elliptic cuts. And if you have elliptic cuts, then this paradigm is essentially challenged because if you separate this into two geometry, then naively you will be computing the d-log form of the two geometry. So you would say that you would expect that your answer is just d-log, a product of d-logs summed together. That's what you would expect. But if you have elliptic part and if you have elliptic contribution, then it's a little bit seems hard to put it into this kind of d-log the description. So we would like to understand eventually, and from this chamber point of view, how do these elliptic contributions contribute? But the first point where the elliptic contribution can start to appear is at 10 points. We're at 7 points, so this is very far away. So we would like to have a simpler problem to analyze this. So we want to have a simpler problem. And of course, if you want to do this for amplitude, it gets very complex. So let's switch an observable. Now, for amplitude, you might ask, why didn't I start with n equals 4? 4 point. The reason is because 4 point, the tree region is just trivial. It's just a point. There's nothing in your tree region. So the way that we want to generalize this is, do we want to look at another observable where the 4 point is non-trivial? There's already a lot of geometry even already at 4 point level. And it turns out that that geometry is going to be associated with another observable, which is correlation functions of n equals 4 supernomial. And so for the remaining of the talk, I'm going to talk about the geometry associated with this object. Now, since this is probably the first time the correlation function appear in this conference, so let me indulge myself and just give a brief description. So basically, we're looking at the correlation function of 4 operators. It also has a perturbative extension in terms of tooth coupling. We just care about the functional form. So in general, at L loop, the answer basically looks like this. It has a factorized, a universal part in front times a loop integral. The loop integral is actually something extremely simple. It's actually what is called the f function. The f function is the integral in position. This is position space, but this integral enjoys the property that, so of course it depends on 4 points, x1 to x4, but there's also L loop region that you're integrating over. So it's basically there's 4 plus L points inside here, inside this loop integrand. And this 4 plus L points are the integrand that you get here actually enjoys a 4 plus L permutation symmetry. Okay, we're not the first that actually try to attempt to write down a geometry associated with this. Actually, people have already tried before, and just to jump to the very end, it'll be interesting to understand the relation between the geometry that we introduced and what they have there. But we're just focusing on 4 points. And it turns out that just like n equals 4 supernomials, you like to talk about the super amplitude. We also like to talk about the super correlator. So we want to talk about everything in superspace, in chiral superspace. And the object that we'll be focusing on is what is called the potential here, which is you get this the super correlator by acting sufficient number of derivative on your potential. The reason that you have this is just associated with the fact that these are BPS operators. So you already know that it satisfies certain number of supersymmetry. That's why you know that the function can be written as super derivatives here, acting on the potential. Okay. So long story short, Eden, Heslop, and Mason in 2017 already introduced a geometry associated with this f function. And there they also introduced the notion of bosonized twisters, which involves a usual twister, which gives you the information of the bosonic degrees of freedom. And then the super twisters contracted, and the bosonic part, the bosonized part, where the fermionic degrees of freedom are contracted with a fermionic scalar function. And this, so that this becomes boson. So this is exactly like what you do for n equals 4 supernomials. And then the function that you have is just you integrate over these phi's and you get your correlation function. Good. So this is the thing that would be interesting. And we'll be interested in this geometry here. So this function here. So the proposal is, so the setup is, okay, so let's start with 4 points. So each point is described by two twistors, a bitwistor. We're going to define our kinematic region by requiring that these bitwistor is positive. Okay, so ij is just so there's each bitwistor has two of them, so there's actually four twistors here. So this is like a 4 bracket, and we require that this is positive. So this will be the region that we're looking at. So we're looking at 4 points where their separation are all space like it in a sense. You can gauge, so this condition has a left GL4 and right GL2 to the 4 power symmetry. So just by this argument, you can see immediately that you only have 2 degrees of freedom under this condition. This is not surprising. These are the 2 cross ratios. At 4 points, you only have 2 cross ratios. So essentially, we're defining the space for this for the 4 point, and therefore it should be just 2 degrees of freedom. And these 2 degrees of freedom you can identify with the usual Z and Z bar for people who are working who are more familiar with doing correlation functions of 4-point functions. Okay, very good. So so therefore, if I'm going to think about a geometry for it. I'm going to think about the form for this space, and this space will be 2-dimensional. So great. So already we're at a much more simpler context where the tree region is actually just a 2 form. So how do we define the tree region? So already we have that we wanted each 2 points to be positively separated. There's actually an extra condition that we're going to impose for various different reasons. The delta square, which is actually exactly the square root that Mark was talking about, because as you can imagine, now we have 4 points, and these 4 points are not null separated, and therefore this configuration is basically the 4-mass box configuration. That's another way of viewing it. So that's why you will get these delta, which is related to the square root that Mark is discussing. But if you plug it into this, if you plug our parameterization into this delta, you'll see that it's just C1 minus C2 squared. So it's always positive for real R. So since we're going to define our space for real with these real parameterizations, so we're going to impose that delta squared is bigger than 0. So this is our tree region. So great. So we have a construction where we have the tree region, and then immediately we do exactly the same thing. At each point in this tree region, we attach a loop geometry. So we attach the AB xj is bigger than 0, and then of course the self-positive condition. So we are back at the amplitude construction, exactly the same thing. We have a tree region, which is a 2 form, and then at each point in this tree region, we attach a 4L form. And we're asking, okay, first of all, do we actually see that there's this chamber structure appearing, and what are the natures of these chambers, the chamber forms, and we can ask many questions. Okay, so first let's just compute the form. So the form for just the tree region, you can directly compute it. So as I mentioned, so these are the boundaries, 1, 2, 1, 3, 1, 4, 2, 3, 3, 4. I mean, these are all the local boundaries. And then we also have the delta square has to be bigger than 0. You just throw in your parameterization, do cylindrical decomposition, then this is what your form look like. This region actually splits into 2 pieces. So either C1 is bigger than C2, or C2 is bigger than C1. This is actually, it turns out that these 2 pieces are actually a double cover of this region. So you actually have 2 different forms that are related by C1, C2 interchange. Now, this doesn't look like anything that is familiar, but you can always do, so this is in the 2 dimensions, the subspace within that particular frame. You can restore the GL4 times GL2 invariance by using something similar to the Amplituhedra map by uplifting into Y. And then within Y space, you can now read off directly what the form is. So I won't go into detail, but this is what the tree form essentially looks like. So we have STU, sorry, I should mention STU is not your Mandelstam STU. STU is just x12, x34, x14, x23, and x13, x34. These are not null. The points are not null separated. So these are not actually 0 at the moment. Okay, so you see that. Okay, good. So we see that there's 2 forms. One is for the positive branch, and the other is the negative branch. The 2 branches again associated with the double cover. And so good. This is our Tn. So this is the form that you get for the tree region. And now we're going to look for chambers. So in general, the structure that we expect is that first we compute it in this two-dimensional space, and once we find chambers, we're going to compute the chamber form. There's going to be two branches associated with that double cover, and then we're going to uplift it into X space, and then the Y space, and then the potential is just going to be the sum over the tree chamber form multiplied the loop chamber form, and the loop form associated with each chamber. So let's look at 1 and 2 loop. For 1 and 2 loop, there's actually no chambers yet. So that means the entire Tn, the form actually looks the same. So it's a direct product at 1 loop and 2 loop. So again, we have the tree chamber form that we computed. The 1 loop chamber, the 1 loop form is exactly the same for across the entire tree region. And for those of you who are familiar, you can see that this is exactly the four mass box integral. Addressed with these, you can say that these are your Jacobian factors associated with the maximal cut, and there's a plus and minus associated with the two covers. You take this, you multiply it by this, you can see that this piece is going, because of the plus minus, is going to cancel. In the end, you get this answer here, where G1, 2, 3, 4 is just a four mass box, and this is exactly the one loop correlation function that you get from perturbative computation. At 2 loop, it's the same. There's no chambers again. So the 2 loop form, I just directly compute the 2 loop form over across the entire Tn. The 2 loop form is the same. It is the same across. So you just have one object here. Now it's 2 integrals. So this is essentially, you can write it as the square of 1 loop, whereas this is essentially the 2 loop double box integral. And then you take the 2 loop form, you multiply by the tree chambers that you have here, or the tree chamber form, and you get exactly the correct 2 loop answer. One of the interesting thing here is that notice that our definition of the geometry is this, right? We basically, if you forget about this part, you basically just have, and this is again a bitwister, so you just have two tree bitwister as being positive. The loop bitwister is also positive, and the loops are mutually positive. And therefore, in a sense, just without this delta square bigger than 0, this definition is already permutation invariant. Permutation meaning that I can interchange the tree points with the loop bitwister, and they actually satisfy the same condition. This is actually a permutation invariant definition. Of course, the way that we construct the form breaks this symmetry, because we first start with our T4, then we on this T4 we let the loop regions start to grow. We grow these loop fibers, so that actually the construction breaks this symmetry. But in the end, the final form we get, if it's correct, you can see that the whole permutation symmetry is reproduced, is restored. Which you can actually check. Now comes the punchline. At 3 loop, we start to have chambers. So here, again, because of the fact that the tree region is very simple, it's just 2-dimensional, so we can really understand the chamber in much more details here. So at 3 loops, we have 6 chambers. The 6 chambers, I'm just going 1, 2, 3, 4, 5, 6. The boundaries of these chambers are very simple. They're actually just the relative ordering. Remember, STU are all positive. Again, S is 1, 2, and 3, 4. These are the distance, or you can view them as x1, 2, x3, 4. So they're the different orderings of the 4 brackets that you can have. And so this is the cross ratio space, and this is it. So this region is empty, because this is delta square smaller than 0. So here at 3 loops, we have 6 chambers, and you can compute the chamber form now. The chamber form is now going to be distinct. Of course, the sum of the 6 chamber form is going to reproduce my original tree chamber form, which you can check that it indeed does. Moreover, the chamber form reflects the boundary of the chamber. For example, this is the R1 chamber, which is here. This is the chamber form associated with here. So this is R1. You can see that R1 has 2 boundaries. It can be 2 codimension 1 boundary. One is S equals to T, and one is T equals U. If it's T equals U, then it's neighboring the R2 chamber, which is here. And if S equal to T, it's neighboring the R3 chamber, which is here. Then the fact that you have 2 chamber boundary is reflected in that the canonical form that you associated with that you compute for the chamber have these chamber boundaries here. Of course, the delta square you can associate with extra constraint that delta square has to be bigger than 0. This is a chamber boundary for R1. This is a chamber form for R1, and you just do permutation, and then you can get the chamber form for all the other chambers. The loop form is much more complicated, but you can compute it. So again, as I mentioned, so how do we know that there's 6 chambers? How do we know that? Well, we compute each point in here, and then in practice, what we do is that we put numerical points and we compute the loop form. And then we have a dual conformal invariant basis of integral. And then we cast the chamber form that we computed here on the basis of that integral to determine what that loop form actually looks like. Yes?
So the boundaries of these chambers, the physical cuts of the
Yeah, okay, very good. So yes, in some sense, yes. So you can ask what happens at the boundary, or what determines this boundary. And if you look at the final loop form, so basically the loop form will usually so this is a little bit compact the way that we've written here. So for each chamber let's say R1. There's going to be ST and U. There's going to be a particular order of ST and U that determines what is sigma 3, sigma 2, and sigma 1. So for example, sorry, I should have written this in a little bit more detail. So for example, for chamber R1, you have S. This will be sigma 1, sigma 2, sigma 3. And then you just plug it into here. And then, for example, AS, if you change S to T, you just do the exchange of these indices, and you get all the different chamber forms. Now, this part, you notice that this part doesn't depend on any sigma. So this part is actually universal for all chambers. What this means is that these integrals, which we list here, their maximal cut is always positive for each chamber. So that's why it's there for each chamber. On the contrast, these C integrals, these C combinations, which involve these E and E prime is just this propagator that's missing. These actually appear in different chambers in different ways. And the reason that they appear in different ways is precisely because the cuts for these integral actually for some chambers are positive and some chambers are negative. So basically what happens is that at that boundary, these cuts actually change sign, or they can go to 0. So that's what the chamber boundaries are in this point of view. At the boundary, if you compute the maximal cut associated with these integrals, it actually starts to cease to be positive as you cross the chamber boundary. Yes, so that's basically what I say here. So you can be understood through the positivity of the cuts. So this is very complicated. You can actually, there's a lot of consistency check that we can check for these loop forms. For example, as we say that two chambers merge. They share a boundary, so one of the consistency conditions is that their loop form associated with chamber 1 and loop form associated with chamber 3, for example, they share the boundary S equals to T, so the loop form better agrees, and indeed they actually agree. So you have two loop forms and they merge to the same loop form at the codimension 1 boundary. You can go to boundaries where it actually goes outside of delta square bigger than 0. So for example, one of the boundaries, T equals U here, if you look at R1, you go to T equals U. In principle, it should be shared with R2. It also has this T equals U boundary. But if you compute the delta square, you'll see that it is smaller than 0. So one of the things that you would expect is a change, because your geometry is not defined there. So actually what you will see is indeed that the chamber form vanishes at these boundaries. Now, of course, we're not the first to compute this. I mean, we're just giving a geometry that gives you the answer. The answer is already computed a long time ago. And if you look at the answer that was computed, it is given very similar to amplitude with certain leading singularity times pure function. So these are polylogarithms. And so we see that this structure is now reflected in our geometry in precisely this picture of you have chamber form multiplied by your loop form. If this is related to this separation, then you expect that these leading singularity is just a linear sum of the chamber forms. And indeed, it is that is exactly true. So these are the leading singularity written in our parameters. These are the leading singularities that people have computed for this tree loop for this correlator. And if you just pick any one of them, you can see that it's really just a linear combination of the chamber forms that we did. Okay, now, of course, the reason that we started to look at these correlation functions was precisely we want to understand one of the crucial thing is whether or not this kind of structure of having your chamber multiplied by loop form, how does this incorporate the situation where your amplitude actually has elliptic functions in there. And that's precisely what we wanted to see here, because we know that this answer at 4 loops has an elliptic function. And it turns out, so this will be something, because the for loop is a little bit more involved, so this will be a longer paper that will appear probably later in the year. So we verify first that the chambers that we computed at 3 loops no longer segregates at 4 loops. So that's enough. So at 4 loop is the same set of chambers. They just grow their own their own loop form. So there's no new chambers at 4 loop. So we verify this. More importantly, there's even though there's no new chambers, so that means that all of your leading singularity is still just these rational functions, of course, with this delta associated with the square root. But actually, we know that the for loop actually has an elliptic integral. And I just show you the elliptic integral here. So this is A, B, C, D is a loop region, and 1, 2, 3, 4 is the external. So each one of these lines represents a propagator. So this particular for loop integral, you can verify it just by performing 14 cuts, and you can see that there's going to be elliptic. So you're going to have an elliptic integral remaining. So it is known that this function is actually elliptic. No, so basically what we're saying is that we have rational chambers producing the for loop answer, even though the for loop answer contains an elliptic function. So I think for those of you who work with elliptic function, I think that this is a little bit mysterious, because generally we'll say that when you have elliptic functions, these elliptic functions should be dressed with elliptic leading singularities, where you define the cuts and then you define that these leading singularities are associated with these elliptic integrals that are integrated over cycles. I think that's the current understanding of what should happen. Here we have a counterexample where we have an elliptic function. We have the correct answer, but it's just dressed with a rational function. So it'll be very interesting to understand what is going on here, and hopefully we can report our understanding in the near future.
So what's the argument of this elliptic function? What's the argument?
Oh, it's the cross ratio. It's the 2 cross ratio. The 2 cross ratio.
So
yeah.
What is the elliptic curve? Is there like elliptic curve somewhere they define?
You mean how do we know that it's elliptic?
Yeah.
Yeah. I mean, the one way to see that this is elliptic is that you have this integral and then you just go on the boundary. So meaning that we cut the propagators. So once you cut the propagators, a sufficient and deep cut. So we're cutting so there's 16 propagators here. So once you cut 14 propagators, you see that you're going to have a square root. The remaining thing is a square root with a degree 4 polynomial. So you have an integral over a square root of a degree 4 polynomial. And so we know that that's an elliptic. Yes.
Regarding the leading singularities and the chambers, since I see that you have some minus signs and plus or minuses, can you interpret that as an actual tiling of the leading singularity? So the leading singularity is a region that is a subregion in the tree region, right?
Yeah, yes. So that I think
what happens in the amplituhedron. You have
yes.
every leading singularity is the image of a positor itself, and it's either a tile or something with high intersection number, and that your chambers, it is supposedly maybe a union of some chambers.
Yeah, I think that even though we started with this questions to try to answer started with this construction to try to answer some of the questions that we raised. But of course, as you notice that here in this question, we don't precisely have the amplituhedron map. So this understanding of a particular cell mapping to a particular region is at this moment still a little bit absent for this picture. So I mean, that's one of the sneaky things that I did, which I probably didn't motivate here in the beginning, which is that in the amplituhedron, we're used to thinking about that we have cells and then we have amplituhedron map and then we have this Y space. And notice that I change into a description of this directly in kinematic space, precisely because then I can talk about things without referring to an amplituhedron map. And so without referring to like whether or not the region are images of positors of certain Grassmannian. And this later on, Jakai will talk about the amplituhedron associated with ABJM, and this way of going, like avoiding talking about the amplituhedron map can lead us to can let us do things without understanding exactly these problems. So that there's an advantage, but in the end, we always encounter certain issues that are precisely associated because that we don't have amplituhedron map, and eventually we still need it to understand what's going on. So that question about this tiling is essentially we need to go back and see whether or not we have an amplituhedron map to actually discuss that.